Bueno, muy buenas tardes para todos. Bienvenidos al coloquio divulgativo del Departamento de Física. Tengo el privilegio de presentarles al profesor Frederick Corbán, quien nos va a dar la charla el día de hoy. Frederick es un experto a nivel mundial en cosmología, lentes gravitacionales, cuásares y agujeros negros, galaxias alto redshift, evolución galáctica, procesamiento de señales, data science y en exoplanes de vez en cuando. Frederick es una persona muy importante a nivel mundial y tiene un tema muy interesante para compartirnos. La charla va a ser en inglés y Frederick me ha pedido el favor que las preguntas las hagamos al final. Entonces, Frederick, gracias por estar con nosotros en el coloquio divulgativo del Departamento de Física y por favor puedes proceder con tu presentación. Muchísimas gracias.
Okay, thank you, Alejandro. So I will give the talk in English. We'll try to share my screen, have the pointer ready. Okay, wrong one. Okay, that should be the talk. Okay, do you see the talk and the pointer?
Yeah.
Okay.
We see.
Yep. Okay, so I will talk, so not about all the things you see there on screen, but about some of it. So we'll focus on cosmography with time delays in strongly lensed quasars. So I will explain all this jargon in a few minutes. So the talk will be mostly about lensing, but not only. It will be about time domain astronomy. So that's why you see light curves here in the background. And it will be also on how to use these different instruments. Maybe in that specific talk, I wouldn't speak much of SKA and LIGO, but I will speak a bit of James Webb, the EELT, so the extremely large telescope built in Chile, and LSST, which is a time domain telescope. But I will also try to present for a few minutes a telescope we want to build in Switzerland to follow up LSST. Time delays and lens quasars. So why is this important at all? So you may have heard about the H-naught tension between the early and late universe. So the difference in H-naught values you find when you measure H-naught from Planck, for example, from the cosmic microwave background, or when you measure H-naught from local probes like supernovae or like lensing. So lensing is a local probe in the late universe. So how to summarize this in one plot? So here you have the expansion rate of the universe as a function of redshift. So redshift is here. So redshift 0 is here. That's the redshift of the cosmic microwave background. And that's the look back time. So here you're at Big Bang, 13.7 years before now. And that's present day. So when we say late universe, it's now. It's when the universe has its present age. And early universe is when we are close to the Big Bang. Now, you can measure H-naught in two different ways. Either you measure it in the local universe. So for example, lensing and supernovae do that. And that's the green point you see here. Or you measure it from the CMB. Now, if you measure it from the CMB, you're at redshift 1100. You observe this kind of map, that's the whole sky in microwave. And you see some small structures there. And in this map, there is a hidden structure. If you take the power spectrum of it, you obtain this thing. And what you see is a peak at an angular size of about 1 degree. And that corresponds to the sound horizon at the epoch of recombination. So when photons and electrons decouple, the signal there in the map gets frozen or apparently frozen. And what you see is the superposition of many sound waves in the primordial plasma. And they're frozen around 147 megaparsec. So that gives you a standard ruler at that redshift. So a typical scale that sustains an angle of about 1 degree. Now, if you take a cosmological model, so a flat lambda CDM, for example, so flat universe called dark matter, and you extrapolate this back down to redshift 0, of course, you will intersect the z equals 0 line, and that will be the h naught value. So this curve is h of z, and h naught is h of z at redshift 0. But what you measure, in fact, is h of 1100 extrapolated back to 0. That's why we call this the inverse distance ladder. So now, of course, if the green point here, the local point, is correct, and if the black curve is correct, then the purple point and the green one should superpose. Otherwise, means either that the green point is wrong, or the pink point is wrong, or the curve is wrong. So there are many possibilities for this discrepancy, and that's in fact the current problem. What we call the H naught tension is the tension between this value and this value. So the tension between when H naught between when you measure, so the tension in H naught, sorry, when you measure it locally or from the CMB extrapolated back to 0. So if the black curve is wrong, then we may have to invoke new physics. If the points are wrong, then maybe the measurements are wrong. So that's the whole importance of the thing. Now, we have one method to do this is to measure time delays in lens quasars or lens supernovae. We'll see this as well. So if you have an observer, and if you have a lens here and a quasar that is lensed by the galaxy, you can have different optical paths to the from the lensed images to the observer. So you have one here, and you have another one here. And then if the quasar undergoes some photometric variation, this will be seen with a time delay at their arrival at the telescope. So for two reasons. One is the difference in length between the optical path. Second is the gravitational delay of photons passing in one position in the potential well of the lensing galaxy and the other position here. Because you don't probe the two optical paths, don't probe the potential well at the same place. So there is a differential gravitational delay between the two lines of sight. And that's why this method depends on a model for the lensing galaxy. And of course, of the distances between the different things. So dl, distance to the observer to the lens, ds to the source, dls from the lens to the source. So of course, you never see the unlensed quasar. You only see the lensed images. Now, if you live in a large universe, then the time delay will be longer than in a smaller universe. And the time delay is inversely proportional to H naught. So in a big universe, H naught is small, time delay is long. And in a smaller universe, you shrink the time delay. That means H naught is larger. Now, if you write this in equations, the time delay depends, of course, on the redshift of the lensing galaxy, which is here. Then a ratio of three distances, they're angular diameter distances. So it's a ratio of distances, so that contains 1 over H naught. And then, so delta, so that's not the Laplacian, it's a difference. It just means delta as a difference of positions between the lensed images. You also, so that's relative to the source position. So this one is unknown, you never see it. And there you have the potential well of the lensing galaxy. So the idea here is from imaging, you constrain well this quantity. So where, that's lensing information at the position of image 1 minus the same thing at position 2 or 4 images sometimes. And then you have a free parameter, and then you have the mass model for the lens. So if you manage to do this, measure the lens redshift and measure the time delay, then you get H naught through this distance. Now, what's important is that it's really a single step method. It's not a ladder like supernovae, Cepheids, and so on. And it's also completely independent of any other method. So that's why the method is getting more and more popular, because it's really a true independent probe of the late universe cosmological probes. Now, to do this, you need 3 steps. First, you need to measure the time delays. Second, you need to measure the mass slope at the position of the lensed images. And third, you need to measure the contribution of everything along the line of sight. You know, this galaxy, all these galaxies with their dark matter halo that leaks. And there is always a bit of mass leaking from all the things from redshift 0 to the redshift of the source that leak in the Einstein radius of the main lens, which is here. And that will change the time delay, of course, because it changes the overall lens model. So you need these 3 steps. So step 1 is to measure the time delay. So I have an example here of lens quasar with 4 images. That's taken with the space telescope. So of course, from the ground, you don't get this image quality. But the goal is to measure the time variations of these things and get the time shift between the curves. So that's what you get. You know, it takes some time to obtain these light curves. You see the years passing there. So that's the different light curves. Once you get them, you shift them in flux and in time. You see the shift being done here, and you get the time delay. So you see it's of the order of a few weeks, usually between the lensed images. Now, something you see there is that the curve match, but they don't quite match. And that's because of stars in the lensing galaxy moving in front of the lensed images. And when they move, they produce what we call microlensing. So that's lensing variations due to the stars. So it's flux variations due to the stars moving in front of each of the lensed images and producing, let's say, some second order lensing in there. And this is very slow. You see, for example, the orange curve here takes a long time to join the green curve here. It takes years. So if you have a way of observing quasars at high temporal cadence to catch only the intrinsic variation of the quasars, then you can measure time delays on a much shorter time scale, just because you sample well the sharp events and don't try to measure then the very slow events due to microlensing. Because this is a superposition of 2 signals, the intrinsic variations of the quasar and microlensing. Now, to get these light curves, what we do is to use image deconvolution. So that's an example. That's a typical ground-based image of one of our objects. That's the deconvolution. That's the Psf each time. So the point spread function, the way the blurring by the atmosphere of the data. And so you do this deconvolution game and you obtain the light curve I showed you before. So for, in this case, 1, 2, 3, 4 lensed images. And that's decontaminated from all the stuff around. So that's the host galaxy of the lens quasar. And that's the lens that you saw in some of the first images. So I was saying, okay, observe at high cadence. So this is the long light curves of the object you've seen before. This is one observing season. And this is not a zoom on the same data. It's data taken at high cadence with a bigger telescope. So over 1 year. And you see immediately the time delay is striking. And in fact, since the season is short and you sample very fast the light curve, then you don't see any microlensing variation. The microlensing variation I was mentioning would be, would take the full season across. So this we can do now at the 2.2 meter Glacier, observing every day. And we also do it for many objects. I see 1, 2, 3, 4 objects. We have like 6 new in this paper. And that's done in typically 30 minutes of exposure per night. And the precision we have on the light curves is typically 3 millimag RMS, down to magnitude 17, 18. So essentially, in terms of cadence and depth, it's essentially already better than LSST for a single epoch of LSST. Okay, so now we can measure time delays in 1 season. Something else I wanted to show is a program we have at the VST to do, in fact, the same, except that now the field of view is 1 square degree, and the telescope is 2.6 meter, and it's internal. So we got the program to observe 12 fields, so 12 lenses, which is also 12 square degrees. The total program is 2,000 hours of telescope over 2.5 years. And this gives a lot of byproducts. Now, each day we have 30 minutes of exposure per field, down to great seeing, and for 12 square degrees. So that's in fact like getting LSST type of data, several years before LSST. Of course, it's a one-time experiment. We don't do the full sky, but it gives an idea of what will be in the LSST data. So just to give a taste, so we have, of course, our lens quasar in the center of the field, but we have a number of other quasars that we discover in these fields thanks to the variability. And then we also require that these things are visible in the infrared. We discover supernovae, typically 30, 35 supernovae per month in these fields, and variable stars. So there are lots of byproducts using these data. So we use different imaging to analyze this. So you see here the differences between different epochs. So you see a time series of a small galaxy with a supernovae, and that's the pairwise difference of the images at the same dates. And you see the supernova blowing up here. But it's very faint. This one is like down to 24th magnitude. Okay, so we measure time delays in about a year per object. We are doing this in 10 years before. And we have all these nice byproducts. Once you have this, you're not done. You need to measure the slope of the lensing galaxy that you see here, but you don't see its dark matter halo. You need to measure the slope of the lens at the across here at the position of the lensed images. That was the angle theta in the first equation I showed. So you, of course, model the lens using, can use different things, elliptical power laws or elliptical Navarro-Franklin-White plus baryons. So we do the two things. That's the area. So that's a cut across the lens. And that's the mass, the surface mass density of the lens. For the power law, that's the pink line. And then of course, you may think, well, power law is not a good description of a galaxy. It's better to take an FW plus baryons. And we do this. So in this case, you have the halo in red, the baryons in green, and the sum of the two is the blue curve. And where we have lensing constraints, essentially the two things agree. So that's quite reassuring. You use a simpler or a more complex model, they converge to the same thing. And that's what will drive the value of the time delay of H naught. So this slope gives you, turns you time delays into H naught values. And then third ingredient, contribution of the line of sight. So there we can do, it's very hard, of course, because you need to integrate all the mass up to the redshift of the lens quasar. So this star here is the position of a lens quasar. That's the HST field of view in two filters. And what we do here, so we do two things. One thing to estimate the mass, the statistical mass along the line of sight, is to count galaxies, so galaxy counts. So if you do this and compare, let's say, the average density of galaxies across the field to, for example, the Millennium simulation, you can see which lines of sight in the Millennium simulation that have the same number counts of galaxies as the data have overdense or underdense lines of sight. So we measure this in terms of kappa. So kappa, so typically if you have zero means your line of sight is as dense as in the Millennium simulation. 0.05 is 5% denser, 10 is 10% denser. And that's the correction you need to apply to H naught. So it's a fairly important one. Now, the probability distribution function we get for the line of sight by counting galaxies is the gray curve, this one. And if we use weak lensing, so that's a completely different method. That's how the very distant galaxies all over the place here are distorted by all the stuff in their foreground by lensing. So that gives you the weak lensing mass along the line of sight. So the red area are where you have more mass, and indeed you have more mass where we also have our lensing galaxy. And then you plot the probability distribution function for this mass, and you find essentially the same as for galaxy counts. So this is pretty much under control. So of course, the two things can be wrong, but it's two very different techniques giving the same results within error bars. So now the number here, remember the number here is the correction you need to apply to your H0 value due to the line of sight, and that's a percentage. So if we do this, that's our measurements for 7 lenses in the sample. That's the H0 value you get. You follow all the steps, measure the delay, do the lens modeling, and then estimate the what we call the convergence or the, let's say, average surface density of the mass along the line of sight. So you measure this line of sight, apply the correction for it. What you get is a flattish correction. After correction, the H0 values agree. So of course, we don't arrange that this correction is flat. It just happens to be flat. So it means it's probably correct. So this is before correction of the line of sight, clear correlation. After correction, no correlation. And that's the effect here. So you see, if you have 0.05 here, you're wrong by, your H0 is wrong by 5% if you don't correct for the line of sight. So that's a really critical step, which is also why we put so much effort in doing the weak lensing, doing the galaxy count, and so on. Now, if you do this, so we do this in a blind way. So it means that in none of the steps in the analysis, we see the H0 value we will get. So all this is blinded. That's centered on 0 during the analysis. Then we unblind and we publish things as they are. And so far we did this 6 times in a row, plus we added a new lens recently. Actually, that should be 7. Okay, anyway. So if we do this, that's the typical number we get. 74 plus minus 1.6 for a power law model. And if you take a more complex model, essentially the same thing. So that's our current result, if you believe galaxies are power laws or stars plus narrow Franken-White. Now, if you compare this to, so let's know the tension now. If you compare this to CMB, here is what you get from the CMB. Here is what you get with 7 lenses. So the number is slightly different than what I showed before, because that's 7 lenses and not just 6. So that's the point we get. That's the point we get with 6 lenses, and that's shoes. So that's the supernova program. So since supernovae and lensing are completely different probes, we can combine. And if you do this, that's the typical point you get. And now, if you compute the tension between these 2 points, that's 5.3 sigma. So the two measurements are now significantly away from each other. So that supports the tension. So of course, that makes people quite happy. So that's, Adam Ruiz presenting these results, in the pre-COVID time where we could go to conferences. So Adam is super happy here because, not only our point agrees with his, but he really likes this cosmological probe because it's completely independent of any other. So that's why, this plot was really well perceived at that conference, and even people started to call, said, no, this is not a tension anymore, it's a crisis. So that was what was published in a paper right after the conference. Okay, so future avenues. So where do we go with this? So we can do several things to constrain the data, and at the same time to relax our models and introduce more degrees of freedom. If we don't believe galaxies are exactly narrow Franken-White plus stars, you can parameterize this with something we call in lensing lambda MST, which is in one single parameter. Here you kind of summarize a broad variety of shapes. So of course, if you introduce such a parameter, you will increase your error bar, so you need more constraint to constrain your lens models. So that's why we applied for time on the James Webb Space Telescope. to, of course, get very high resolution imaging of some of our lenses, actually only one in the first proposal. But we also want the spatially resolved kinematics of the lensing galaxy, because that constrains the lensing potential, the different way than lensing. So it's complementary, it breaks some degeneracies inherent to lensing, and that brings us to 4% precision on H0 with one single lens. So if you have 10 lenses observed with James Webb and with time delays, potentially you get to 1%. So that's one avenue. Let's see if we get the time. Second avenue is to say that lenses live in the same world with or without time delay. So they're drawn from the same parent population. And then we go for a hierarchical Bayesian analysis of the whole sample that contains lenses with measured time delays and lenses that don't have time delays, but for which you can have resolved kinematics with telescopes that are less costly than James Webb, that can be done with a VLT, maybe with the EELT. So if you combine 40 lenses with time delays to 200 lenses with no delays, but kinematics, then again, you reach H0 to 1%. In a quite different way than with the James Webb kinematics. So these two things are quite complementary. And of course, a third avenue is to use lens supernovae. So with LSST now, there should be several lens supernovae discovered each year, but you have to be there with follow-up time. And presently, no, there is no LSST. So we do this with GTF, which is the Zwicky Transient Facility. We also monitor monthly known lenses, waiting that a supernova blows up there. And we have this BST large program where the probability of finding a lens supernova is not negligible. So of course, we have target of opportunity time, which is approved on VLT in case something blows up in a lens system here. And I will speak later about this SWAT project that can be used to follow up these kind of events. So what's great with supernova is two things. So first, the supernova disappear after a while. So the bad news is that you have to be there to follow up with spectra immediately. The good news is that when the supernova is not there anymore, you can study the lensing galaxy easier. And second thing, if the supernova is a type 1a, then you have two cosmological probes in one, the supernova itself and the lensing effect. So that's how I see things. But it's not, you are not done. You need to also improve lens models. So what's a lens model? So how do we do, when we try to determine this psi term I showed in the first equation? Essentially, that turns into a lensing operator that you apply to a source. So a source can be a galaxy like this. You lens this through an operator, you convolve with the Psf, you add the light of the lens and some noise, and essentially you should recover your data. So that's how the data are constructed. So usually people use, for S, some kind of analytical representation. We choose to have many more degrees of freedom and represent this as a full image decomposed on a wavelet basis. So wavelets, is a bit like a Fourier transform, but also with the spatial information that is kept. So if we do this, that's the type of reconstruction. Oh, sorry. So I should come back here and say that in the first step, before solving this big problem, we just ignore this and work on data where the lens light has been subtracted. And we also, in the first step, assume that F is known. So there is somehow a lens modeling tool that has been used to estimate it, or that you know it from if you've been using only simulations, and we reconstruct the source, because that's one of the crucial steps in the lensing problem. Once you have this, you can then extend the problem to the reconstruction of F and to the reconstruction of G here. So that's lens light, and that's the mass in the lens. Now, results on real data. So that's the SLAC sample of lenses where the lens has been subtracted to make the problem easier. And that's what you reconstruct of the source. So this is in fact the unlensed image of this each time, where the lens light has been pre-subtracted. And you see, the quality of the reconstruction, that's the residuals each time, and that's what you were getting with the standard reconstruction with shapelet plus Celsic. So you say that the source is a Celsic profile plus shapelet, which is a bit like the Haneke polynomials. You should see this as an harmonic decomposition of a light profile. So this is anyway fully analytical, and this is fully numerical. So just a grid of pixels. Now, we go a bit further, take now a simulated lensed object, now as seen with the European extremely large telescope. So that's this 39.5 meter telescope that is being built in Chile. So that's a simulation with the actual Psf, so the actual point spread function of the telescope. And that's the model, the model fit to the data with wavelets or with shapelet and Celsic. So you don't see much difference there, but when you invert the lens equation, it's kind of striking. This is the galaxy that has been used to produce the lensing features here. That's what you would get with fully analytical profiles for the source, and that's what you get with wavelets. So very close to the truth. Now, on top of that, this takes 7 minutes CPU versus 3 hours here. And that's an image of 2000 pixels across. So I don't know how many people here are familiar with lensing, but usually source reconstructions in lensing problems are of the order of 100 pixels across, not more. So here we really go for super high resolution. Now I told you, we've been subtracting the lens light, but no, before doing the modeling. So, and that's not an easy thing. So you can, of course, fit models, light models on the data, or you can use a more general method, which is here called generalized morphological component analysis. So it looks like a complicated word, but in fact the principle is simple. You have data. The data are made from different filters, let's say 3. Now, in each filter, you see blue things, you see red things, and there is a mix of the different components. So this is like, it's a schematic view of an image in one filter, another filter, another filter. And you say that each image in each filter is the combination through a mixing matrix of 2 sources, or 2 channels, a red one and a blue one. And that matrix contains, in fact, the SED, so the spectral energy distributions of the red and of the blue source. So you give relative weights of the different sources through the SEDs, and then you retrieve the data. So that's the input, the output. No, sorry, the input. The output is this, and that's the SEDs. So either you know them, or you can also optimize over this matrix, and then in this case, that's called the dictionary learning problem. And of course, since we like wavelets, we stabilize the problem. It's not that we like wavelets, but it's really necessary to stabilize the problem. It's a heavily ill-posed problem, so you need to regularize your solution, and we do this with wavelets. Okay, so the output is the red source, the blue source. That's an example of it. So now you say that the data here is a weighted sum of the red and the blue things. So the red thing is here, the blue thing is here. That's your output once you have minimized this big function. And that's the result of the process. Now you take the original data, you remove the blue source. That's what you get, of course, the red the red part of the data. And if you do the original data minus the red source, then you get the blue things, which happen to be usually lens arcs. So we'll show an example here of a galaxy cluster that we processed in that way. So you see all lensing feature, lots of blue things. Not everything blue is not necessarily lensed, but here the assumption is that we separate the blue from the red things. So if we do this, here is what happens, if you remove the blue channel, the blue source, and here is now what happens if you remove the red one. So you see how well the deblending works. And there is no model fitting involved here. We have never used any fitting of double, triple Celsius or whatever to the objects. So that's one possible processing we would apply to the data before doing the modeling. And of course, we can do the modeling including the lens light and solve everything simultaneously. But for now, we go step by step, subtract the lens and then do the lens inversion with the sparse lens inversion I showed you before. And by the way, this code can be used for other applications. You deblend things or you decompose things into a map of pixels that have the same SCD. So for example, here you have an HST image in one filter, a red one, an HST image in a blue filter. You have a collection of HST images. And you say that the collection of HST images is some weighted sum of the red channel and the blue channel. And you mix them. So in the end, what you end up with is a map of all pixels that have the SCDs you decided in advance, either a red one or a blue one or anything you want. So this resembles this, of course, because it's the blue channel and the bluest image in the dataset. And this is the same in red, although these two things here look alike, but they're not quite the same. In fact, what you did here is to decompose the different stellar populations in the galaxy. And each stellar population, in this case, has some arbitrary red SCD or arbitrary blue SCD that you can decide. So you can study, galaxy, star formation across galaxies, dust content, gas content, things like this. You have to choose the SCDs to do your favorite analysis. Then something interesting in any astrophysical problem is Psf reconstruction. So to inverse a lens model, to do weak lensing, to do stellar photometry, you need to know the Psf of the instrument. Now, if you observe from space with one single filter, which will be the case of Euclid, for example, you don't have colors. You have one single broadband filter, which goes from here to here. And that's different stellar SCDs across the field. So first thing you want to do to compute the Psf is to classify stars. Usually you do this with a color magnitude diagram, but you don't have colors. You have one single band. So what we do is to train a neural network on different stars of different types and therefore colors. And since it's a space telescope, the Psf is diffraction limited, so the Psf doesn't have quite the same shape depending on the color of the object. That's what you see here. You have a red object here, a blue object. These two things don't have the same Psf. And that's the differences you have between different stars of different stellar types. So what we do is to train network on known stars or even simulated stars. And then we test the real images and do stellar classification. So when validating the method, we try this on full simulations. And usually the result is that we can classify stars to half a spectral class using one single filter. So that will be crucial for Euclid Psf. Now, Euclid will observe a lot of lenses. We will want the Psf everywhere in Euclid. You will need to observe, to use all the faint stars to reconstruct the Psf. So you need to classify them. So Gaia did it, of course, but all the Gaia stars will be saturated in Euclid. So you need to classify stars fainter than Gaia with one single filter. So just to illustrate this classification, I show an example here. So I don't know if you've seen a color magnitude diagram done in one filter, but that's one. So to do this, we take HST images of an open cluster in two bands. and we train. So we make the actual color magnitude diagram in 2 bands, and then allocate a color to each star and each PSF shape. And then we take a different open cluster in one single filter, and we do 2 experiments. First, we do the color magnitude diagram by classifying the stars with one single filter. And that's the blue thing, the blue diagram here. And then we compare to the diagram that you would have using 2 filters. Of course, we selected a cluster that had 2 filters in the HST archive, but we used only one with the machine learning method, and 2 filters to get the reference. So let's say the true color magnitude diagram. And you see, it's pretty much the same diagram. There are some differences here, but overall, if you want to classify roughly the stars, you can do this with CNNs and one single filter like Euclid. So that's a pure imaging problem, but it's fundamental in addressing almost all the other problems that Euclid will want to answer. And then, the final part of the talk, I wanted to present a project we have here, and that's called SWAT. So SWAT is the Swiss Autonomous Telescopes. And the goal is to devise a small network of telescopes worldwide, and that would do some follow-up of LSST, SKA, Euclid, and LIGO. I didn't speak at all of gravitational waves here, but once you have a telescope that is very flexible, observe at high cadence in many filters, you can go and try to find the optical or infrared counterparts of gravitational waves. Of course, same thing for the radio, and same thing for the million transient LSST we'll find in almost every night. So science cases for that, before even thinking of the building of the telescope. Of course, you understood that lens quasars will be one of the main science drivers of this telescope. Lens supernovae as well. But of course, non-lens supernovae, hypernovae are important science goals. Fast radio bursts, if they happen to have any optical or infrared counterpart, are also important. Same thing for any radio transient in the SKA. And of course, gravitational wave transients. And additionally, you can spot space junk in the sky, so all kind of human-made debris, and study, the impact of space environment on Earth. So all this with the same telescopes. Now, how to do this? Now, or let's say one way to do this. So that's the telescope we want to follow up, gravitational waves, radio here, and optical here. Either you build your own telescopes. That has been done near Munich. That's a 2-meter telescope that you can buy, for a few millions to any, well, actually, no, not to any, but to one single company in Germany. Or you can recycle a telescope that exists already. So, for example, the VST at Paranal will be decommissioned in a year from now. So ESO and Italy, because Italy is the owner, is looking for partners to use this telescope, and of course to fund this telescope. So the idea is to have a network of telescopes. One would be large, like a 2 to 4 meter in the south, because SKA and LSST, so the main big surveys in different optical in different domains are in the south. And you want 7 optical bands, 3 infrared bands, fairly large field of view, possibly with a small integral field unit, but that's extra. You don't really need this on this big telescope. And you want to monitor things to an hourly or daily cadence. So if you want to do hourly cadence, you need telescopes around the world. Daily cadence, not necessarily, but you want at least this, because the cadence of LSST will essentially be 1 point on the on any light curve every few days in the best case, and sometimes not even in the same filter. So if you want light curves like the ones I showed before, you can't do this with LSST. And you also want rapid response to transients. That's why you need also some kind of intelligent systems to point the telescope and coordinate between the telescopes and coordinate between the science goals you want to reach. In one night, you have to coordinate radio follow-up, gravitational wave follow-up, LSST follow-up. No, you want a scheduling system that is really completely automated. Now, on top of this, you also want a small network of small telescopes, typically 30, 50 centimeter each, a very wide field camera. And that will be used, of course, for the brightest objects and very rapid response. Sometimes the objects that have a large uncertainty on the pointing, like gravitational waves. And you want a fast tracking system. And that's what you want to find and track human-made space debris. Oops. So you probably heard of the Starlink network, and that's the disaster produced on the DCAM camera of the Dark Energy Survey. But in fact, even on our small VST data that we have, half an hour exposure per night, that's typically what you find. So what CNN find in terms of space junk on such an image in one single shot. So, and the telescope is sensitive like a SST to a 10 centimeter piece of metal in geo orbit. And that's now before massive constellations of satellite have been launched. So the idea is really to use the telescope, to use SWATs to do both science and space debris tracking. So of course, the space debris tracking will be more efficient at twilight and at dawn because of this solar reflection. So you don't need even to use the science time of the telescopes to do this project. So what will be the setup for such a thing? So of course, nothing is frozen here, but you need at least 6 sites to do round-the-clock monitoring. You want a big telescope in a great site. So next to LSST would be a good place in Chile. That would be because now the LSST would be the main client of SWATs or vice versa. You may want also another one in South Africa next to one of the SK array, maybe in Australia. So the big one would be here, and then the rest will be the smaller telescopes. So of course, in the north, we don't have any big survey, but you still want at least 3 small telescopes there to follow up at least the space debris. So I put sites here, but they can change. Now, one site would be great on the campus here because of all the technological developments associated to the project. One here where the Zwicky transient facility is operated, one in Majdanek where we have observations already for our time delay business. And all this will be operated with an intelligent scheduling. So essentially, the telescope would learn from the streamed data of the different observatories what to target in which filter, at what time, from which site. So there you need all this network of telescope, the intelligent scheduling system, and follow up the main science observatories of the next decade. So it's not the same as, for example, Las Cumbres Observatory, if you know it. So it's also a network of telescopes, but it's operated as an observatory. So you apply for time and you get your time once for your program, and that's it. This thing would be operated as a survey and as a service to the community to follow up the main facilities in the optical and in the radio, but and of course in gravitational waves when the detectors get more sensitive. Now, okay, this is more because it's part of the talk for EPFL here. So the funding scheme for this is essentially some European funding here, private sector, since we're in Switzerland, MPA Garching would participate, and in fact the Swiss Army would likely pay for the tracking of space debris, especially the undeclared ones or the moving ones while they should not be moving. So in fact, the space junk is also the business model of the telescope. Just just to give you an idea of how interdisciplinary would be this project. So if we do it at EPFL, SWAT would be the central part in a constellation of partners. So one is, of course, University of Geneva, because we are next door. We are in Lausanne, they are in Geneva. They have expertise in instrumentation. They've been developing tons of things for exoplanets, so they know how to do instruments. We have imaging experts at EPFL to process the data. We have the eSpace Center, which is interested in explicitly interested in space debris. Of course, the Swiss Data Science Center, which is typically to do machine learning type of project or big data project. There will be a wealth of projects for students even before the data come. Robotics, to make the telescope not intelligent at this point, but automatic and robotic. But then the next layer would be to add artificial intelligence. So we have at EPFL a Center for Intelligent Systems doing this. So they develop autonomous cars, these kind of things. So why not autonomous telescopes? So we can decide almost on their own what to observe in the best possible context, given changing scientific goals. Scientific goal now is not the same as in a year from now, or it's not the same as before the discovery of such or such thing. So you have to adapt your science goals to your telescopes and vice versa all the time. I think I will stop there. So future of time delay cosmography. So it's probably LSST won't do this properly because of low temporal cadence. So you need something like SWAT to do it. You need to do it in multiband. So I didn't mention the fact that, for example, microlensing was chromatic because the source size depends on wavelength. So in fact, you need multiband observations to remove completely microlensing. You need, of course, new large sample of lenses that will be done with Euclid and LSST, essentially. Lens supernovae will come only with LSST, but you will need things like SWAT to follow up immediately things that blow up. So SWAT is not the size of LSST, but LSST observes like 90 seconds per night and per pointing. Here we can afford half an hour easily. So we can do the LSST follow-up, even though we have much smaller telescopes here. And then, of course, if James Webb works, hopefully, and the VLT works also, especially its adaptive optics system, we can get spatially resolved kinematics of lens galaxies and improve even further our H-dot measurement. So that's one avenue. And the other avenue is this hierarchical Bayesian analysis of time delay and non-time delay lenses. And Euclid will provide especially the second type of lenses. Okay, I think I stopped there. So I don't know if I should stop sharing or not, or
Okay, Freddy, thanks a lot for your very interesting and nice talk. I invite to all auditorium to open the microphones and give a warm clap to Frederick for this nice talk. And we have time for questions of all person in the auditorium. Please free ask your questions to Frederick.
That's right. Just try to rearrange my screen.
It's possible to write the question at the chat. Is another chance.
Hola. Hello, Fred. I would like to ask more about the wavelet decomposition system. That was, yeah. Could you repeat that part about how you are separating blue from red?
Okay, so I go back to the slide. So you should see the slide. Do you see my cursor also now, or?
Yes.
Yeah. Okay. So there are two. So I use this in two places. So one is here. That was the one, or you were thinking of this other one?
Yeah, this other one.
This one, okay. So what we say here, in fact, is just that these are images each time. So here I simplified by putting some kind of 1D image. But in fact, this line is, for example, the HST red filter and an HST green filter and an HST blue filter. Actually, I don't show here the different images in the different filters. That would be it. Each image you see in the previous slide is an image in a filter. So that's one, that's two, there can be more. So that's the data. So of course, in the data, all objects contribute, the blue ones, the red ones. Or even you can have green ones if you want. You can say, I will decompose the data on the basis of red, green, and blue sources. So this is an image. This is also an image, and this is just a few coefficients. Now, the wavelets are the way you represent the data. So here you see a red, we call it source, a red image or a red channel. You should see it as a collection of different scales like this. So if this is the red image I showed in the previous slide, for example, you decompose it as small scales plus bigger scales and a bit bigger and a bit and so on, and you end up here with a coarser scale. And then if you do some summing of these 6 images, you retrieve the original image. So you take the wavelet decomposition of the original image. These are the 6 scales we consider. Then you take the weighted sum, where the weights are the wavelet coefficients. You take the weighted sum of these 6, and you get an almost perfect reconstruction. So sometimes what people do is that they threshold the noise in each scale, and they use this decomposition to denoise images. But there are many different applications. Now, the way we do this here is that we just have a cost function, which is the difference between the data and the combination of the different sources through this mixing matrix, and where each of the sources is decomposed on wavelets. Now, the technicality to minimize the cost function is a bit tricky, because you can say my image is a number of pixels described by wavelets, and you do the minimization in pixel space. Or you can say I will minimize not my pixels, so the pixels won't be the parameters, but the wavelet coefficients. And the wavelet coefficients are the 6 weights you give to each image here that are used to recompose the signal that you previously decomposed into wavelets. Okay, I don't know if this explains or.
Okay, yeah, just one small follow-up question. So
Yeah.
it works so far mostly on HST data, right? Or
Well, it has been used on ground-based data as well.
okay, so as long as you have the images, the multiband images to create the mixing matrix.
Yeah, you
okay.
need. So it really depends on what you have. The more bands you have here, the better. Of course, it's getting harder and harder to get more bands. And then, of course, if you can describe your data with the minimum number of sources, it's also better because it's less degrees of freedom.
Okay, Ferry, thanks. The students are writing some
you.
questions. Let me formulate the questions. Carlos Alberto Calvachi asks, do you think that the current cosmological models are authentically increases or further efforts are needed to improve experimental data?
Sorry, so you mean if the models are getting better than the data or the opposite?
Carlos, can you speak to clear your question?
Hi, Professor. I'm referring to that you at one slide said that models there was some difference between some models and the unprecise data. In one slide, it was mentioned that uh, there was a certain graph and experimental discrepancy. Yeah, I'm
This one?
specifically exactly. I'm specifically asking you if you think that this is showing some kind of profound crisis on the theory, or that you certainly believe that this error bar could eventually decrease. That's my question.
Yeah, so actually no one knows the answer. But let's say what we can say, let's see, can show this slide. So that's a picture that Adam Maurice likes to show about all the early universe measurements of H naught and the late measurements. So in this talk, I focused mostly on supernovae, which is this point, and lensing, which is this point. And I was arguing that it's because they're completely independent, which is true, but I can still be both wrong. Now all the rest of late universe probes tend to agree. They have larger bars so far, but that's, for example, the use of surface brightness fluctuation, which is a method completely different than the rest. Still, it's based on the calibration with Cepheids. Water masers, independent of the rest. This one truly, but the error bars are big and it's dominated by peculiar velocities of galaxies because they're really nearby. Mira stars can be used as standard candles as well. Tip of the red giant branch here. And here you have the Cepheid program of, that's the tip of the red giant branch program of Carnegie. So all this, so it's true that all these methods kind of rely on each other somehow. But, they all converge there. So it's becoming more and more unlikely that all this is wrong altogether and landing in the same wrong place. No, it's too many miracles to accomplish. And then same thing for CMB. The experiment is pretty well controlled. So I think there is no escape. There is indeed a tension there. So the curve I showed here for flat lambda CDM probably has to be revised. Then, of course, the next problem is, now it's easy to move the curve. You add degrees of freedom, and then you fit everything. The next question is, does it mean anything? You have a new curve, new degree of freedom, but it's not because you introduce things like early dark energy, late dark energy, so you change the curve here, or you change the curve here because you invoke some yet another dark thing, and then all the points agree. So I would say there is absolutely no answer so far, which is why, in fact, this problem is getting more and more serious. You see nowadays like 1-2 paper per day on trying to explain the tension, assuming it's correct at all. So no clear answer there. No, really, we can't say right now new physics or problems with the measurement. No, as always, it will be a bit of both, I guess.
Okay, thanks, Frederick. Alejandra Mesa asks, how long does it take to release the image once you have taken the data?
So with which telescope?
Alejandra, please speak with our invited, the Professor Frederick. Okay, any of them.
Okay. So typically, so let's say these data that we take with the Euler telescope, essentially, at the end of the night, it's in Lausanne and reduced. For the 2.2 meter, it's a bit more complicated because it's large format CCD. And for the VST, it's super large format CCD. So it takes like a day to arrive in Lausanne. It's all processed. Now we have an automatic pipeline that check if there is a new image taken each night, fetch them from ISO, reduce, and do the mosaicing and so on 1 square degree. So it's really fast. It's not seconds, but it's maximum of the order of the day. Now, when it comes to observe with SWAT, so this network of telescope, really we need things to be very fast. So not only we have to transfer the data, reduce them in an automated way, but we also have to do the science in an automated way. Because you want to react, you want the network of telescope to react according to what has been seen in the data. And you don't want an army of humans to inspect all this data daily. So that will be the challenge for SWAT if we manage to build it.
Excellent, Frederick. I have a question. With respect to the you about the variable stars detected with the 2.6 meter at VLT telescope. I have a question. What is the is a high quantity of new variable stars detected using this data, or is a byproduct with the small sources?
No, it's I would say actually we didn't check just because no time for now. We didn't check if all these were new, but they're pretty faint, and they're usually outside the Milky Way. I mean, outside the plane of the Milky Way, because our lenses are, of course, not in the Milky Way. So these are probably halo stars, faint halo stars, so pretty distant Cepheids. You see the magnitude here, is 20.
Yeah, and you classify these variable stars using machine learning techniques or some other technique?
No, for now we don't do anything with them. We just plot them, and that's about it.
Okay, perfect.
If you want to have a try at it at some point, you can have them. It's just that for now we are a bit drawn under the mass of data. So we are really after. First thing we want to do is if we see a lens supernovae. So that's taking a lot of effort. Then quasar, and then for us, Cepheids variable star are less our business, but I think there are very few data of that quality for variability of stars.
Yeah, it's very interesting to have this type of variable stars.
I think there is Cameron Lemon is a postdoc here, and he's been working on these light curves like hell. Then there was COVID, so everything was stopped for a year essentially. And now they're resuming observations, but at some point soon, in fact, we'll have a paper with all kind of variables in this field. So our first paper won't really be time delays; it will be a catalog of variable stuff.
Okay, thank you, Frederick. Thanks a lot. We have time for more questions. Okay. Okay. The students and the auditorium don't have more questions. Frederick, we want to say you thanks again. It was an excellent talk, and we are very grateful with you for your time, and we give all of this interesting talk. Please open the microphones and give another more clap to our conference today.
Well, thank you.
Okay, Fred.
And maybe see you in person sometime.
Yeah, you are welcome at Uniandes all time.
Okay.
Have a nice night. Thanks, Fred.
Thank you.
Thank you. Bye bye.
Thank you. Bye.